Alright, let's begin with a recap of what we saw in the previous video. We discussed subgroups in the last video. We saw that a non-empty subset of any group G star gets the extra status of a subgroup if it satisfies the 2-point verification or the 1-point verification properties. And we also looked at a couple of interesting results. If H and K are two subgroups, then H intersection K, the set of all common elements, also qualifies to be a subgroup. We also saw that the union is not always a subgroup. The union becomes a subgroup only when a particular condition is satisfied. We saw one extra question which says the center of a group is always a subgroup for any group G star, plus the obvious result that you already know is that the singleton set containing the identity element alone is also a subgroup of G star. We call it as the trivial subgroup. Now with that recap, let's go to the first important topic to be discussed in today's video: order of a group. Now just like we saw what is called as the order of an element, we also have a notation called the order of the group, which clearly stands for the number of elements in the group G star. You just count them and that becomes the order. We have one word of caution here: the order of a group and the order of an element are different. Like in an example, considering the fourth roots of unity, like 1, minus 1, I and minus I, the group has 4 elements, so the order of the group is 4, but order of 1 is 1 because 1 raised to 1, the smallest power of 1, which gives you back 1 itself, is 1. 1 power 1 is 1. Order of minus 1 is plus 2 because minus 1 squared is 1. Both plus I and minus I have their orders as 4. So the order of the group and the order of the element of the group are not the same concept. And in case your group has an infinite number of elements, you call it as a group of an infinite order. Now in this light, we have an important result called as the Lagrange's theorem. This theorem helps us to eliminate certain sets which will never form subgroups of a group G star. If you can recall in the first conditions which are to be satisfied by a subset to become a subgroup. Now Lagrange's theorem makes our job easy. It clearly eliminates those subsets which will never form a subgroup. The theorem statement is very simple. If some non-empty subset of G star actually forms a subgroup, then the order of the group G is a multiple of the order of the subgroup H. Like in the example below, consider 1, minus 1, I and minus I. The set, the singleton set 1, is clearly a subgroup, the trivial subgroup. It has only one element, so order of H1 is 1, and 1 clearly divides 4, which is the order of the group G. Similarly, H2 containing only 1 and minus 1 is also a subgroup. You can verify that. It has 2 elements and the order 2 divides 4, which is the order of the group G star. On the other hand, look at the last example. H3 has 3 elements, 1, minus 1 and I. This subset is clearly not a subgroup because, for the simple reason that it is not closed. Minus 1 and I, when you operate both, the result of the operation minus I is not present inside the set. So this doesn't qualify to be a subgroup. But you can do a simple verification of the same stuff. You can see that there are 3 elements in this subgroup, the subset. 3 doesn't divide 4, which means H3 can never become a subgroup of the group G star. So Lagrange's theorem is going to give us a very simple idea, a simple test to find out whether a subset can actually become a subgroup. We'll have a look at a couple of more examples so that the idea sinks in. Okay, if we consider the group Z12 plus 12, then I've listed down 7 subsets below. H1 is definitely a trivial subgroup containing only 1 element and 1 divides 12. H2 contains 2 elements, and you can verify that it is actually a subgroup. 2 divides 12 again. H3 containing 3 elements is also a subgroup. I leave this part of verification that H3 is actually a subgroup to you. It's a very simple thing. You can always do that. And once again we see that the order of H3, which is nothing but 3, clearly divides 12. The same happens with H4. The same happens with H4, which has 4 elements, and H5, which has 6 elements. Both H4 and H5 are subgroups, and their orders, namely 4 and 6, are divisors of the order of the actual group, which is 12. 6. H6 in fact has 6 elements, but it is not a subgroup. I want you to understand the observation here. H6 has 6 elements. 6 clearly divides 12, you know that. But this subset does not form a subgroup simply because it doesn't have the identity element. That's one of the reasons. There are other reasons as well. But I wanted to make this observation and register this in your minds. And look at H7. H7 is not a subgroup because it's not closed. I add 1 and 1, I don't find 2 in the same set. So 2 is absent, therefore H7 is not a subgroup. But I can always verify this because H7 has 5 elements and 5 never divides 12. 5 doesn't divide 12. 12 is not a multiple of 5, and this is enough for me to eliminate that H7, which is a subset. This subset can never become a subgroup of the group G star. So how does Lagrange's theorem help us? Like this. If some non-empty subset H of G star is such that the order of the group is a multiple of this order of this subgroup, then H may be a subgroup. I tell you that H may be a subgroup. I'm not giving you 100% guarantee that H will be a subgroup. H may be a subgroup, H may not be a subgroup. But the second condition here is very strong. If the order of the group is not a multiple of the order of this subset, like in the last case that we saw on the previous slide, then H can never be a subgroup of G star. So Lagrange's theorem actually helps us to identify what can form a subgroup or what cannot form a subgroup in a pretty simple way. Okay, next up we have this concept of cosets. In order to understand important concepts like normal subgroups and the pseudo theorem, familiarity with cosets is required. So we'll just introduce this idea of cosets before we move further. A coset is actually a subset of the given group G star, which is constructed in a very particular way. We'll need one subgroup H of some group G star and one element A of the group G to construct this special set called as the coset. So the definition goes like this: let H be a subgroup of G star. A coset is actually formed by operating an element of A with every element of this subgroup H. So as a simple example, we'll have a look at the group Z6, set of all reminders when you divide any integer by 6, which is operated upon by the addition modulo operator. And let's pick a subgroup H containing 0, 2 and 4. Clearly this is a subgroup, you can always verify that. Now I have actually written down two different cosets of this subgroup H. In the first case, I add 1 with every element of H. I get a subset of G. I get a subset which is 1, 3 and 5. And I've added the element to the left of every element. I add this element from the left. There is also the other possibility where you add the element from the right. So I've added 4 to every element of H, but this time the addition happens on the right. So 0 plus 4, 2 plus 4 and 4 plus 4. give you that subset having 4, 0 and 2. So we give special names to these two different kinds of cosets. We call them as the left and the right cosets. If the element is operated from the left, it's called as a left coset. Example, that's what we saw. And at the same time, if the element is operated from the right, it's called a right coset. We also saw an example for that. Now with this, we are ready to define the idea behind a normal subgroup. A normal subgroup is going to be an additional status given to a subgroup. We see that actual definition here. A subgroup H of a group G star is called a normal subgroup if a left coset of H has the same set of elements as its corresponding right coset. Basically, if the left coset and the right coset have the same set of elements, if they are the same sets of elements, then this subgroup H gets the special status of a normal subgroup. So if we can consider Z6 plus 6 again, the same example. When I add 3 to every element of H from the left, I get 3, 5, 1 and 1. When I add 3 to every element of H from the right, I still get the same set of elements. So this means that H here actually gets qualified as a normal subgroup. So this thing is pretty easy if our group is abelian, because the order of the operation doesn't determine the answer. So one conclusion that we can make is that if G star is an abelian group, then every subgroup of G star is by default a normal subgroup. But this abelian nature of G star is not a mandatory condition to be satisfied. G need not be abelian always. We give you one example for that too. Consider G star 1 minus 1 I minus I j minus j and k minus k, the group of all quaternions. We know that this clearly is not an abelian group, but we consider one subgroup of this G star, call it as 1 minus 1 I n minus I. Surprisingly, this subgroup H of a non-abelian group G star actually gets the extra status of a normal subgroup. Now when I operate the element j on this subgroup from the left, I get j minus k and plus k, but I also get the same set of elements when I operate the element j on H from the right. I get j minus j, k and minus k in some different order, which is not in the same order as jh was, but the elements still are the same. So both cosets have the same set of elements, which means by definition this subgroup that we have considered here also gets the extra status as a normal subgroup.